Hello there, hope you're doing okay. Welcome to the wonderful world of the radio frequency and electronics engineering. On the bench for repair today is a power supply, only a small little power supply, a linear one as well, not a switch mode one, that's coming for repair. This power supply has come in with some other items for repair. Apparently the voltage on this, from what's been reported, is excessive, coming out the two front terminals. It should be 13.8 volts DC. Although it's only a small power supply in size, it does actually boast quite a current rating of 10 amp constant and 12 amp surge, which is unusual for a power supply this size. Normally supplies I get that's at this size only rated to around about 6 amps maximum and 8 amp surge, so it'll be quite interesting to look at this further. So what we'll do, we'll plug it in, but before we do that, we'll just have a quick look round it, make sure there's nothing obvious. I mean, obviously on the side here it looks like as if there's been some damage there with the look of it coming in and out. There's no screw in there. Just as I was turning it round there, you could see that that front panel's coming out there, so it must have had a bit of damage. There's a bit of a crack there as well, and this screw's missing. So we've got 3 screws in there anyway, and then on the rear we've got the usual fuse mains cable coming in, 230 volts AC at 50 hertz like we use here in the UK, 2 amp fuse, and then under here we'll have the series pass transistors, which is what we've had on other power supplies fail. If you look at my earlier videos, we've got some repair videos there of really high current power supplies that deliver 30, 40, 50 amps and upwards, where these transistors have failed. So it's quite a small heat sink. It doesn't seem to be fan cooled from what I can see. And then on this side all the screws are there, and obviously the plug's not in bad nick. There's no damage to the cable from what I can see. Everything seems fine there, so we're safe to plug it in, I think, as safe as we can be. You can see underneath there the mounting screws for the transformer, because obviously, as I said earlier, it's a linear power supply. So yeah, everything looks okay. It's just that observation there on the side with it having a loose case part, and obviously the screw coming out there. So it's quite a heavy supply, I must admit. It's a good few kilos is that in weight. So we'll plug it into the voltmeter behind, and we'll see what output we get back shortly. Okay, so we'll just switch it on and connect these cables. Have a look, see what we can do. We've got the voltmeter just behind there, and as we can see there, we're getting a 24 volt output. And when I switch it off, I don't keep it on for long, because sometimes on the board, the filter board that connects to these two banana sockets, they have low voltage capacitors rated about 16 volts DC and quite a lot of power supplies. So obviously the voltage being 20 odd volts, it might have already blown those or potentially be going to blow them. So, but as you can see there, we're getting 24 volts DC output, which is way above what it should be. So obviously if connecting anything there that needs 13.8 volts DC, obviously going to blow up whatever is plugged into it. Normally most power supplies, if a fixed output, have a protection, a crowbar circuit there that triggers when the voltage raises above a certain level, about 15 volts if it's a 13.8 volt power supply, and it'll just short the output and pop the fuse. But this power supply, from what I can see, has not protected itself in that way. So even now, the capacitors are just discharging slowly, and we're still at 14 volts, even with the supply off for some time. So yeah, it looks like as if there is obviously definitely an issue there. At least we confirm the fault that the customer's reported, which is high output voltage. So let's whip the case off and have a look inside. Obviously we switched it off before, unplugged it before we remove the case, because we don't want to get fried. It's quite easy to forget about that. You'd be surprised how many people forget to unplug something when they switched it off and then start whipping the lid off, and yeah, interesting times ahead when you do that. So anyway, we'll remove these screws, Looks like as if it may have had a bit of a drop, this power supply, or something like that's occurred where the damage to the case front's occurred on the other side, or it's been banged against something. But we'll have a look, see what we can do to rectify that and repair the plastic. But obviously it's had a bit of a knock there for that to be cracked. But yeah, pretty unusual. Right, just one more screw after this one, and then we can get into it and see what's inside, see if there's anything obvious. Right, aha, there we go. Right, so let's have a look. One big reservoir capacitor down there, right down there, which I can see. Obviously we've got the large transformer with the various taps coming out with the look of it. Bridge rectifier, looks like it's mounted on the board with separate diodes down here in this section. Certainly there's something there. That's probably for the low current supply for something. There's no PCB on the front either, or anything mounted on the front. And yeah, from what I can see, looks a bit how you're doing inside, but it's not too bad. We've obviously got 2 series pass transistors on the back, so let's have a closer look. Okay, so the architecture, it looks pretty simple. If I just turn it this way a little bit so we can see, it looks like we've got a separate tap output to this rectifier down here. Which looks to me like it's half-wave rectifier, because both diodes are connected together on the on one side for the positive output. That's the little smoothing capacitor for these diodes, obviously to smooth the rectified DC, and that's, I think, the supply then for the voltage reference circuit and the driver. And then of course then these taps here, the main current high voltage output, which then goes to these bridge rectifiers down here. So we've got a few diodes down there, so there's a couple of supplies which is coming off here, and then these big chunky diodes are the ones that the bridge rectifier form the 4 larger diodes. I'm not sure what the other one does, unless that's a part of the rectifier for something else. And then we've got a smoothing capacitor down at the bottom there as well, the large reservoir smoothing cap, which is on the output of these diodes. We've got a transistor mounted on this heatsink here, which is soldered at these 3 connections. So I suspect that that driver transistor drives these 2 power transistors that are bolted on the heatsink at the back. And that's really it as far as the rectification and smoothing is concerned. The capacitor's not really big, but I suppose it'll do the job. And then down there, of course, we've got the potentiometer for setting the output voltage, possibly, or the current fallback. I'm not sure if it's got any fallback control on this power supply. I might have to remove this board and have a closer look. So one of the faults that could occur here, a couple of things really. It could be the voltage reference circuit for the driver has got a fault, and thus the driver's driving the 2 power transistors on the rear here at maximum voltage, and they're passing you know, all the voltage through from collector to emitter, because the base might be full on. Or it could be this transistor's popped and it's giving basically a collector emitter short and obviously driving these 2 transistors. Or it could be that one of the power transistors on the back, as we've had with previous other repairs, where it goes collector emitter short, and it only needs that to occur on one of the transistors, not on both, for that fault to occur. So there's various things that we can look at here in order to go further. I think we'll just remove these 2 screws and just bend this board up and have a look a bit closer at the board, see if we find any burned out components or any signs of any damage or anything like that. So we'll do that now. Okay, so we pull the circuit board out as far as we can, because these wires are quite tight here, but we've got some burning marks here which we can see just in this area here, it's all sort of got hot, which I think is down to the voltage reference circuit, which we can do a bit of a zoom in on. But there's definitely something going on down there, because I don't know whether you can see that very well on camera, but if you look at this this resistor here, it's a bit chalky. It's got an appearance as if it's burned up or starting to burn up. That, I think, this diode here, I think is the Zener diode, or not 100% certain. It could be this glass diode here. That could be the Zener, and that's just a protection diode just for that. But it may not be, because I've had Zener diodes at a high current that are in that package as well as being a rectifier diode. But I won't know till I get in a bit further. We've got the transistor down there here, which obviously feeds the output, amplifies the output of a Zener circuit, then to provide the voltage reference drive, and that then in turn can be adjusted somewhat with this potentiometer to the driver transistor down at the bottom there, which is way down here, mounted on a heat sink, which you can hardly see. So yeah, we've got some kind of a voltage adjuster. We've got a Zener circuit here. That resistor does not look too happy. Obviously we've got the separate supply coming for the voltage reference on its own from those two diodes, and this reservoir capacitor which supplies all the voltage reference circuit. We've got another few capacitors here for smoothing, and some other little bits and bobs. So yeah, it does look like as if there's been something going on down there, I must admit. So a bit of a chalky thing, but that is actually quite normal to have that kind of circuit on these, and obviously the heat that generates, because it does run quite hot. So I'm not suspecting there's specifically a fault there, but we'll have to, assuming we can still get the colour code off that resistor, check its resistance to make sure that it's working as it should be, and maybe check the Zener diode. But all in all, that circuit could be working fine. It could be giving a voltage output properly, and then obviously going to the necessary stages. So the fault may not be in that area, but it's certainly something to be taken into account, having that kind of appearance on the body of that resistor. So yeah, we'll take it a next stage further. So rather than mess about with this board and trying to measure on it and things while it's already powered up and with tightness of all these connections, etc., before we delve into that area, which we may not need to do, what we can do as a quick test is we can remove these yellow wires, which are the base connections to the transistors, because the blue wires, when you follow them along, actually connect to the front terminal. So obviously we can remove the base connections and then measure the voltage. Now it would appear to me that would be the best way to measure it, because what they've done, they've actually, when you look down here, they've got the wires going directly from the output of the transistors, the emitters, to the positive binding post. So we're not sure at this stage whether it's these series pass transistors on the back that have gone short circuit or whether they've been driven inappropriately. So best thing to do is unsolder the two yellow wires. That isolates this board from that. We can check the output of this board then on those yellow wires to see whether or not the 13.8 volts or 14 point something volts, which is 0.7 higher than the output we're meant to be getting out, is present on the yellow wires. If it is, then we can start looking at these series pass transistors at the back. But I just want to have a look to see what kind of transistors they are, because quite often they're commonly 2N3O55s. In some supplies you see the higher current ones, which are 2N3771s, which are rated collector emitter current capacity of 30 amps, whereas the 2N3O55 is rated at 15. So let's just have a look and see what we've got on them. So I'll just zoom in, see what's what. They're obviously let's have a look, see if I can see. Let's have a look. Yeah, 2 N3055s, I thought there would be. Yeah, NPNs. So they're NPN bipolar power transistors. So I think now we know that, and that it's not some kind of weird setup, what we can do is just unsolder these yellow wires and then fasten this board back in so it's not going to short on anything, and then do some voltage measurements. Okay, right, where's my pliers gone? I've got them here. So what I'll do is I'll just have hold of that wire and I'll remove that, and do the same with the other one down there, and right, so they're off now. So what we'll do, we'll measure those wires, and now the circuit board's back in situ, we'll put a crocodile clip onto those and then measure the voltage. Okay, so we've got the 2 yellow wires connected to this red lead here, and then that's going off to the voltmeter, and obviously the negative supply is just here. It's getting its negative reference, if you like, from this port here. So when I switch it on, I'm expecting to see some voltage there, and as we can see on the meter behind, there isn't any bias voltage at all going to those transistors, which I find quite interesting, because there should be 14 point something volts in order to bias those transistors on. So that proves that there is a fault on this board anyway. But what we'll do, just to confirm the collector emitter junctions on these power transistors on the rear here are not short circuit, if I remove this this probe and then go to the what is the front of the power supply, keeping an eye on the birdie behind, and what we'll do, we'll just connect up the terminal there, and we are getting 25 volts, nearly 24.59 volts. So that proves really that the without the base connected, the bias, in other words, to those transistors, that they are actually conducting from collector to emitter. The collector being the red wires that connect to the case of the TO3 transistors, and the blue wires ultimately go through to the front there on the red binding post and join together there from both transistors. There aren't any emitter follow resistors, cement types, that we often see on other supplies. So that proves there's 2 faults. One, the transistors at the back, one of them's got a fault because they're both in parallel. It could be both of them have gone collector emitter short, or it could be one of them's gone collector emitter short. So we're going to have to remove those to test them, and then we're also going to have to start fault finding on this board here. It could be that the transistor that's bolted there with the heatsink, that's these 3 solder tags just there, maybe that's gone fizz bang because it's been unable to regulate the output on the transistors there. So yeah, we'll have to look into that a bit closer and perhaps do a bit of reverse engineering. Back soon. Okay, so just to explain further on that then, obviously we've got the bridge rectifier, which is providing our rectification, which is formed by those 4 larger diodes I pointed out earlier on the PCB, and obviously these going off to the transformer. Okay, and then we've obviously got the primary winding there, which is a 240 volts in, and then we've got around on the secondary winding here around about 18 volts, which when it comes out on from the bridge rectifier and then obviously to the smoothing capacitor, then we've got roughly 25, I think it was, 0.6 volts. That ultimately then goes over to what is our 2 transistors on the back of the power supply, which is the heat sink on the rear we were just looking at. And then there are two N3055s in parallel, and they're shared on the heat sink there. The emitters are the blue wires. So this wire here is the red wire, and this one here is the blue, and then the two base wires, if you like, is they are yellow. And then what happens is, then normally on most power supplies there'd be two cement emitter follow resistors before they're then common to go on the output, but on this they've just decided to join them together, and then that's obviously the plus volt output. And the negative obviously reference as well, or 0 volt, that is also this binding post here as well. Now this transistor here will be driven more than likely by another NPN again, and then we'll have the voltage reference then formed, which there'll be some more transistors in line again with this, and then more sort of to amplify the current gain as well for the drivers and pre-drivers. And then ultimately there will be a resistor and then obviously a Zener diode, which will then provide the voltage reference. So again, that will be from its own supply itself in reference. And I've noticed there's a red wire as well coming off the terminal at the front, which then goes back to some kind of current loop. So there'll be some more transistors that are driven off this, which goes then off to the reference side to compare between the voltage reference and obviously what's coming out, and that way then it can regulate the supply as the current drawn from the output and the output voltage starts to decline. Then this can increase the drive in order to then compensate. So there is actually a feedback. Now there's no ICs on the board from what I can see, unless there's one hidden, no op amps or comparators. So it does look to me like as if the situation is purely by transistors. So we'll look further now at these power transistors here. It could be that there's various things occurred, and this transistor's blown anyway, because what's happened is if the output has been dumped into a high current short, for example, or a high current output, then if the base emitters have gone short like they did on one of the other supplies we looked at, then this transistor's fairly low current capacity, and the output current will be driven then to the output, and it would blow this transistor because it wouldn't be able to maintain that level of current. So we'll need to look into that a bit more closely after we've tested these two. So the idea is, because the emitters are connected together and obviously the bases were connected together, by isolating the emitters and the bases, we can then do collector base emitter checks on both transistors independently. So that will isolate them both and then give us the ability to pinpoint which one of the transistors, or in this case it could very well be both of them, that's packed in. So we'll check that next. Right, so we'll just remove these blue wires, these collars, and let's see whether we can get these off, just to isolate. That's it. And same with this one. We'll have to be careful not to burn that wire down there. Move it just to one side, and hopefully we can get on it without burning anything, touching anything else. It's so easy to do, especially when you're going in at like a weird angle. Because on camera, you know, I'm looking at it from quite a considerable distance away, so it's difficult to get the angle right on the soldering iron. There we are. Okay, so we've isolated the base and emitter junction. So the base is on the left there, and the emitter is on the right. So they're all the way. We've just got to be careful when we bend the wires away that they don't touch the mains side of things, because obviously the fuse is down here and mains input, etc. And then the red wires we can leave connected because they just go to the collectors. So we just need to do some testing now with the diode test function on the multimeter to see what these little transistors are doing. Okay, so we've got the meter up here in the corner there as on diode test. So what we'll do, we'll test the top transistor first. So I'll just go between the base and emitter. So we'll make the base positive and the emitter negative, and we should now be getting a diode reading basically between those two junctions, and that junction there isn't. Between base and emitter there should be. Obviously it shouldn't read the other way around anyway when we make the emitter positive and the base negative, and we're not. We should obviously get a reading between collector and base as well, one way around, so we shouldn't be getting anything that way, but that way we should. So yeah, so this transistor's faulty between the base emitter junction, and it is reading okay between collector and base because we've got the diode between collector and base there. Let's just go between collector and emitter. So we'll make the collector positive as it normally would be, and then we'll go on to the emitter. And we haven't got a short between collector and emitter on that transistor. So the base emitter junction of this top transistor is stuffed, and the collector emitter isn't short, but it is okay between collector and base junctions. So reading the correct way around, yeah. So we'll go on to the bottom transistor now, and I just need to bend these down a bit because I can't see what the hell I'm doing. So let me just get on to because the unfortunate thing is the way it's orientated for the camera isn't good for me. I can't see it. So first of all, make the we can still use that connection there because we've got a bus bar going to that bottom terminal, and then that ultimately connects to the other. Because when I go on there, we've obviously got the continuity, so the collectors are joined together. Okay, so if I go on to the emitter on that transistor, we're not getting any reading there, I don't think. Let's just have a look. Yes, we are. We're getting something there. I think it might be a bit of resistance on the there we are, look. So we've got some kind of a leakage between the collector and emitter on the bottom transistor, so it will conduct the high voltage that's on the collector onto the emitter. So now we'll just go onto the base. I can just see it down there, and we'll then go on to the emitter to check the base emitter junction. We've got continuity between base and emitter that way around. Let's just check for the other way around between emitter and base, the opposite way around. Let's see whether that still connects. Yes, we've still got something there. We've got some leakage. So we've essentially got, if you like, a short circuit between the collector and the emitter, and we've also got leakage between base and emitter as well, both ways. So that bottom transistor is not at all happy. So yeah, looks like as if we're gonna have to do something about the bottom transistor anyway. But the top transistor obviously is blown as well. So both transistors are defective, but in slightly different ways to one another. So yeah, the top transistor isn't short between base emitter. However, the bottom transistor is between base emitter. We've got between collector and emitter, which is more dangerous because obviously the high voltage on the collector there, you see, that's reading a diode basically at 558 millivolts forward voltage, so it's leaking between collector and emitter. So that 25 volts supplied to the collector will go straight out onto the emitter. So when we look at this diagram again that I did, we've got the top transistors blown basically. All the junctions really are blown on the top transistor. That's as if it's not there. But the bottom transistor, the collector and emitter junctions are effectively shorted together. So the high voltage is going to pass straight through and out. And yeah, and there's obviously issues there with that as well, with the base emitter too. So if I make the base positive again, because I just forgot where we were with that, so let's just see if I can get on, because these probes are difficult. So yeah, the base, it reads that way around, which it should do, making the base positive and the emitter negative. But if we make the base negative and the emitter positive, we shouldn't get anything. And as you can see, we are. So yeah, there's slightly different faults on those transistors, so we'll have to remove them and obviously deal with that. Yeah, interesting. And then we can have a look at this PCB then as well to find out what the hell's wrong with that. So I might take that off next, and after I remove these transistors on the back, and I may do a reverse engineering job. Might just check this transistor that's bolted there next, just to see what that's doing, and have a better look at that resistor that looks like it's cooked. Right, remove this driver transistor that's mounted on the heatsink and give that a test and just see what's wrong with it, if anything. We'll have to look at that, because that's the last transistor in the chain before it gets to the 2N3055. So we've just got our solder socket and see whether we can remove it easily. Let's have that. Should come out fairly easily. So, having said that, I think that's blocked up again as usual. This is the trouble with these solder suckers. They all get blocked up sooner or later, and then you have to start unblocking them, and that obviously messes everything up. So let's see whether we can find the unblocker tool that unblocks the damn thing. Oh, here we are. We found it. It always happens when you most need it, and times when you don't need the solder sucker so much, then it always doesn't block. But anyway, we'll see what we can do, see if we can unblock it. Got this tool here that's faff about with, and see whether we can clear the blockage. That sounds better. Right, carry on. There we go. Look. Right, let's have a look at it. See what kind of transistor it is. Looks like a bit of a weird number. It looks like, is it a 2SD 0313, something like that. So we'll have to look at that and see what how that's operating. Right, back soon. Okay, so we've got it out now, this device, and we'll just check it on the Atlas meter. So it'll be interesting to see if it works. Just give it a quick test before I go any further. Pull the red wire on the middle. and the blue on the right. Oh, it's a bit difficult to get on these things. Right, okay. Test it. Oh, right, so it looks good so far. NPN silicon transistor. Okay, so the red lead in the middle is the collector. The green is the base, so that goes in that way around into the PCB. So it means this right amp in there is the base, obviously. The middle is the collector, and the green one, yeah, the green is the base. That's right, yeah. So the green is to the right, the red is in the middle, and then the blue is on the left. So it's base, collector, emitter from right to left, BCE. Okay, so just check its parameters and see what it's got. HFE 77, test current IC 250.5 milliamp, base emitter VBE 0.65, so that's good. Test current there 4.64, leakage nothing, so we're back to there again. So right, so that looks good. So what we'll do is we'll just move that out of the way a second and put that over there. What I've done, I've just insulated these wire ends with pulling the sleeves back up so they don't touch anything, you know, obviously. And we can leave those because we're going to be powering the supply up now that the board's back in situ with the screws held in. And obviously somebody's been in this before and marked these terminals here, positive and negative. These look resoldered recently with these connections the way they've been done, and I think that looks like somebody's tried scraping a positive mark in the track there, so it's definitely been looked at by somebody else. So yeah, it's the right hand is base, so this track here on that side is the base, so this is the base, this is a collector, so we should get a supply on there, a high voltage supply, and then that will be the emitter, and that will be the drive then, obviously, for the 2N3055s. And I think if we flip it up, yeah, we can see the two yellow wires down there which go off to the 2N3055s that solder to those two connections. So it'd be interesting to see if the base voltages as get into this, obviously, and what voltages are on here, whether there's a supply on this collector, whether that's gone and there's no supply on this collector. I don't know, because it looks like that track comes round obviously and solders to this and this, which when I look at that is the output of these diodes there and there, and obviously that smoothing cap as well is across that rail. So I've got an electrolytic cap across those two. The transformer inputs are there with the two diodes going off, and then obviously yeah, and this tap here to that part of the transformer, I think. Look of it. So we've got two wires there, and they look like they're black and red wires which are going off to the front two terminals. So yeah, so that's interesting. It comes down here, there's another cap there, and then obviously ultimately it gets to these RC networks and transistor networks that are here. We've got, with a look of it, this looks like the negative side of things, because that's obviously going to the negative side of the capacitor there, yeah. So this is the minus voltage line from that other tap on the transformer. Then we've got two taps again connected here with a diodes going one way this way, so it's like it's halfway rectification. And then we have another track here which I can see this transformer connection at the top. So we've got a diode going that way and a diode going that way, and then also the AC component from this top track also goes down here to there. And I think there's a diode, if I remember rightly, I think there's a diode goes this way, and then it meets with something there, so it's as if it's got its own supply there to that, so we'll have to look at that. But we'll just see what voltages we get on here on the base collector emitter, and then just do a little bit of fault finding around that board while it's powered up. So back shortly. Right, we'll just do some voltage measurements, so we'll switch it on. That's it, it's switched on now. So what we'll do, we'll just measure across this capacitor here, which is from this what appears to be secondary supply, and we'll just go on it, see what we're getting on the meter. Yeah, so we're getting 28.2 volts there. That obviously makes it round to the collector, which is just here, this centre pin for the transistor that we've just removed. That's correct. We'll just go on to the base, see what we're getting on the base there, and I'm not getting anything there. About what, 157 millivolts, 158 roughly. Obviously we won't be getting anything at all on the emitters because the transistor's not in, so there's no sort of resistor bridging anything to the emitter. There's nothing like that. Okay, so we've got that diode just across here, this part of the circuit. So we've got AC getting to this component there, just that little island. So we'll just switch the meter over to AC, and we'll just do that. Volts AC, and we'll just have a look, see what we're getting down to this diode, which is that black silicon diode I pointed out earlier, which we thought could have been a Zener, but I don't think it is. It's 21 volts AC there, and obviously when we go across to the other side to measure what's coming out of it DC wise, we should be seeing something there. 9.5 volts. That's a bit strange, very strange indeed, but we'll have to look at that a bit more closely. And then there's that resistor that's chalky that bridges from there to there. Now we're getting 2 volt. Well, it's even less than that, look. It's just dropping down. So there's nothing there at all. Let's just measure around, see what we get. Nothing there. Can't see any voltage, as you see. That's 1.4 volts there. There's nothing that's 475 millivolts, 72. There's nothing that's sort of standing out as being the sort of kind of voltages I'd be looking to get. So there's definitely something else going on. Obviously we've got a component here that's soldered to the what is the positive supply rail at 28 volts. I think that'll come down to here, and we're getting 23 volts there. Obviously some transistors in this area then that bias, provide a bias output ultimately to this pin, which then obviously biases the NPN transistor we just removed. So there's definitely something strange going on around here. We'll just have a look across these two connections here. So if I go across there and across there, not sure what we've got. Minus 155 millivolts. There's something strange there. But I think that is looks like as if that's somehow something to do with a different part of the circuit to what we're measuring. Very interesting indeed. So I think we now have to start looking in this area now more closely at that black area that's scorched on the other side, which means obviously having to remove the couple of the connections down here in order to then allow the board to flip up so we can see what's going on. But so far it does look like as if the pre-driver stage, the voltage reference area, might have some damage. So let's have a look at that next. Okay, so the plot thickens. I can see we've got a burned out resistor completely there, which has definitely seen better days, for the want of a better word. all the resistor colour code markings are burned off it, so I don't know what state that is in, so we'll have to look at that, maybe objectively. That is the diode we were measuring. We got 20 odd volts on this side of the diode AC, and then about 10 volts DC on this side. That's obviously the series resistance in line with it, and that's the one that had the chalky deposit on it. Luckily, it looks to me like as if we've still got some usable resistor colour code information on that, so we can check that resistance. As for the resistor that's next to it, when you look carefully at that, it does look like as if that's got some kind of a scorching down one side here, but I don't know if that's just a product of the neighbouring resistor burning, or whether this has actually started burning as well, so we'll have to look at that. But that's definitely not good. That does look to me like as if it's in the possible emitter part of the circuit there. And I'm looking at it because we've got the resistor just there, sort of just here. So that potentially looks like as if it's across the output. A resistance across there. So yeah, very strange is that one, very strange. Yeah. So it looks like the positive output from the emitter goes across a resistor, which is soldered across these two terminals. Then obviously to the ground path in that particular way. So I don't know, it does seem a bit strange, does that? Very odd indeed, but yeah, I'll have to see what value that could potentially be. Very, very confusing how they've done that, because we've got this capacitor there across these two connections. That looks like a positive supply that goes to the two terminals at the front. The red wire comes up here, so in other words, it's output of the supply at the terminals. The 13.8 volts is supplied on here, and then gets to this resistor to then go onto here. So it's like a loop back, if you like. So that's interesting. Obviously we've got the negative supply, which is this top black wire, which goes onto here. So again, the output of a supply is present on these two pins, one of which goes up to this resistor, which goes to the emitter, which then obviously goes to the base of the 2N3055s on the back. And then this positive side, or rather negative side there, that goes to this part of the circuit. So that provides all the negative ground path, if you like, from that. And also one of the taps on the transformer goes to this terminal as well. So I'm expecting there. Okay, well, wonderful. We've got a circuit diagram on the internet for this power supply, which I find really useful. I wasn't expecting that. But anyway, we've got different models of this power supply, right the way up to 50 amps as well. The 10 amp model we've got just uses two 2N3055s, but as you can see, the numbers increase in the current output. So does the capacitors and the bridge rectifiers, etc. So interestingly enough, though, I see for 50 amp model they've used 50 times 1N5402s. Surely that price of these components on their own would exceed one bridge rectifier that can deliver 50 amps. It just seems a bit strange. Anyway, looking at the diagram, the two resistors that are burned out is R1 here, which is 220 ohm resistor there, and the other resistor that's burned out is R6, which again is another 220 ohm resistor. They're both gone crispy, and I can't see the colour code on them after I've looked at them under a microscope. So it could be that this Zener diode here has gone short circuit, and obviously all the current from this this diode, the black diode we were looking at earlier, which I've taken out now and I've got it on the bench for measuring. That does look as if it's, yeah, potentially could be faulty, it might not be, I need to test that, but that Zener diode there could have gone short circuit, because that's the only thing in that circuit really. That's a 27k and that's a capacitor. And even if that cap had gone short and this resistance being presented, that's 6.2k, so there's not enough current to cause that to burn out. So it could be that Zener's blown. So that's interesting. So we'll have to check that diode out, but anyway, at least we know what the value resistor is we can replace. But this part of the circuit there does look like it's some kind of soft start, because you get like a pulse. Because when you look at the circuit configuration, you've got that diode, which obviously gets its supply ultimately from the output tap of a transformer. It then rectifies that into what will be a ripple DC. There's no smoothing capacitor across that at all, so it's going to be quite ripply. Anyway, that Zener diode obviously clamps it. We've got 27k in series to obviously 0 volt ground. It comes along here and there's no connections off to any of the transistors or other parts of the circuit, so it goes straight into this capacitor, which is a 0.1 microfarad, and then into this resistor here. So basically on the output of this capacitor we're going to get like a pulse. We're going to get a sort of a quick pulse on, and then it'll die off again. So the moment we introduce a supply into here, this is essentially an RC network which is going to derive on the output a pulse. And it looks to me like that pulse will be fed through that diode, because obviously I think the reason why they designed it is so that the transformer fills up the reservoir caps, and obviously, you know, the avalanche of current it takes to do that is quite immense. So if you have got a load connected on the output, it doesn't want to go straight into regulation driving a high current output while these capacitors are charging, because it's going to then cause potentially a component failure or a current surge which is going to blow the fuse. So I think they've designed it for that reason. So upon turn on, that instant that power's put to the circuit, this then provides a pulse via that diode, which then biases this transistor on. Obviously we've got the VCC line here, which is straight from the transformer, and that's got a pull-up resistor coming down here, which is this R3, to the collector of this transistor, and then down to what would be the ground path. So that pulse is going to bias this transistor on. Again, this has got a pull-up resistor to the collector of this transistor, and then ultimately the voltage is going to derive through this diode to here, which is the base of this transistor. And before we look at this circuit, we'll just describe this bit, but it'll then bias that on. Again, the emitter path goes down to 0 volts, so the collector going along here goes to the base of this transistor, which is like a pre-driver, if you like. There's another series resistor here to then what is again another pull-up resistor with a capacitor. So this is going to have a nice steady state DC supply on it, and again R4 essentially is a dropper resistor via the collector emitter junction of this transistor. So the voltage here is obviously, as part of this pulse, is going to come on into this base of this transistor. It's going to get a pulse coming into it, into this base momentarily upon initial startup. We've got obviously on the supply rail here another resistor in series through this transistor to then ultimately bias this transistor on. Again, that'll conduct through and then bias this transistor here. Again, that'll conduct through and bias the 23055s. That is the transistor we removed a moment ago on that heatsink. Anyway, the output of those 23055s come out and go straight to obviously the emitters of these 23055s, go straight to the output terminals. But what happens is that because that's an unregulated pulse, if you like, or whatever, before that can happen, instantaneously as that pulse occurs and the voltage starts to come up to 13.8 volts, obviously this Zener is going to clamp it, and that part goes via this resistor, that potentiometer, which sets the output voltage, and another resistor to ground. So again, that then again controls this transistor. So we've had the pulse, the startup pulse, for all these transistors, and that's going to bring the output up. But without that Zener diode, this would just have one big pulsed output, you know, it would just go and then back down to 0 again. So the idea is that that pulse comes up to 13.8 volts, which is obviously going to be regulated by this Zener, and obviously then that's set by this potentiometer. So there's some adjustment there to set the output voltage. But once that loop, if you like, has gone round, that pulse, this then comes onto full-time regulation, because this Zener diode then sets the voltage, and then that ultimately goes through these transistors, comes back, sets the voltage again, goes through, and we get like a gain loop, a voltage locked loop, if you like. So the voltage remains locked, which is set by this Zener. And obviously the other resistor, which is R6, which is burned out again. This is again another 220 ohm resistor. Once the output voltage is maintained, obviously at 13.8, there's a current loop here, just in that little bit. So the emitters of these transistors at 13.8 volts is going to feed some current back through into this transistor and back. So as we draw current, or RL, on the output and load the supply, this is going to maintain that sort of current gain in a way. It's going to give it a little bit of help. So that's what that 220 ohm resistor does, it just helps it. So it saves a lot more strain on these transistors further down the chain, you see. But that's burned out. So, and I would expect that to happen if the output was shorted and these transistors were producing a much higher voltage, which they are if we go collector emitter short. We've got 26 volts essentially on the emitter as well. That's going to be a lot higher current and power equation to deal with, and that's going to burn out. So obviously that's it. It's a vicious circle. But it does seem a strange design, I must admit. There's no protection on the output either. There's no sort of thyristor, anything like that, that triggers, say at 15 volts, if there's a fault condition, to blow the fuse or disconnect the output. And interestingly enough, there isn't a protection diode on the output either, because if you've got long wires coming off these output terminals off to something and they're shorting out or sparking together, then the back EMF through induction is going to cause huge voltages to come into this circuit and then potentially damage these transistors and diodes. So yeah, that does seem a likely cause of a failure, if anything. But why they've gone to this trouble to do a soft start, I don't know, because most other supplies just use a delayed relay. So the relay switches the output on after a few seconds or whatever, or half a second. Interesting. So let's have a look at that Zener down here to see whether that's gone short circuit and caused that to burn out. Okay, so I made a little test circuit up. What I've done, I've removed the 3 volt Zener, I think it is 3.6 volt Zener, which was in circuit. And this is obviously in series with the 220 ohm resistor, which we saw earlier, which is R1. Now, it looks like as if this is a 3.6 volt Zener, and I say that simply because its part number is Bravo Sierra 62-3.6A. Now, it's not always the case that the voltage follows the part number. It is in most cases, but I've certainly got some Zener diodes here which the part number doesn't resemble the voltage. So always be careful with that. So what I've done, I've set up a test circuit where essentially we've got a 1 kilo ohm resistor, and then we've got the Zener diode in, and obviously that's 0 volt, and that's plus 20 volt, which I'm applying here, and we're going to measure basically potential between these 2 points here. 0 volt obviously on the meter, and so essentially what I'm looking for is 3.6 volts roughly, around there. So that'll prove whether or not you know, the Zener diode's working. Obviously if the Zener's short internally, then we'll not get any voltage there, obviously, because the resistor will just be essentially across both parts of the supply rail. So what we've got in the background here, we've got the voltmeter, which we can see. So ultimately the goal here is to try and achieve that voltage, to check it. So just go on to the negative there, just try and hold the probe steady so it doesn't move around, and onto the central junction there. So as you can see, we're actually getting 3.91 volts there. So it's only a point sort of about 0.3 of a volt off, so it's tolerable, is that, and nothing wrong with that really. So it's 3.9 volts DC there. Obviously if we look at it the other way as well, just out of interest, if we take 20 volts and obviously minus 3.9 off it, we're remaining with 16 volts, obviously, about that way. So there's 2 ways you can measure it. You can subtract the incoming voltage if you look at it where you measure it across the resistor. You can do that in a circuit, for example, or alternatively you can go between the Zener diode ground, if you like, and then the center tap where the voltage is derived. So you can do that as well. And we have had on some other repairs we've done previously, where we've removed a Zener diode, it's measured, and then we put it under physical strain by pulling on the leads, etc., to position them in the right place. It's then stuff the diode. So sometimes they fail with temperature and they get fragile, the glass structure of them and the internal leads within the device break down with mechanical stress, because obviously all the heat and cooling off cycles that it's gone through over many decades of use. So we'll put that Zener diode back in now, and then we'll remove the other one, which is the other Zener diode is on the top right up here, which is this one here, which is going to be interesting looking at that. I think that's a 12 volt Zener, and then this potentiometer sets the voltage from probably 10 volts right up to 15-16 volts, depending on what rating that can deliver, but I suspect that's a 12 volt Zener. Right, we'll do that now. Okay, so we've got some more 220 ohm resistors, some brand new ones to install to replace the 2 that were defective. I'm just going to check that diode that was coming in, if you remember that black diode when we were looking earlier, from the transformer to the 220 ohm resistor that had burned out, which then goes to that Zener diode we've just mentioned. So we've just got the meat on the diode test behind there. So obviously we've got, just double check this connection, there's nothing that way around, which there shouldn't be, but if we turn the diode around the other way, obviously we should be getting a forward voltage, and we are, which is 571.8 millivolts. So there's nothing wrong with that. So we'll put that back in, and obviously from there we'll put the 220 ohm resistors in, reassemble, and then we're ready then to replace the 2N3055s after we've put all the components back, I think. I might decide to take out some of the small signal transistors that are on there and test those in the transistor tester, just to make sure before we go any further. But I'm just going to remove that other 12 volt Zener now and check that with the test circuit that we derived for the 3.6 volt one. So let's check the other Zener now after I put this diode back. Okay, so this is that 12 volt Zener, allegedly. So we'll just check this. We've got the meter back in DC again. We'll just go on to the ground leg of this lead here. and then there in the middle. Let's see what voltage. So yes, we've got 12.38 volts, so there's nothing wrong with that Zener diode. What I've done as well, just to save time on the video, is that on the circuit board here, what I've done is all the little small signal transistors like these here, and all the others, I've had them out basically. I've had all those out, and I've tested them, and they're all okay. There's nothing wrong with them. So there's one there which is just hiding behind that capacitor one there, obviously, and then there's another one somewhere, I think, hiding around down here. That's it. So anyway, I put some new resistors in, obviously, as you can see, and there's all sorted out as well. So some brand new 220 ohm resistors. Everything's back in now apart from this Zener. We'll just pop that back in, and then it's time to replace the 23055s on the rear, and then hopefully, fingers crossed, that should repair it, I hope. So I've got these transistors out finally, these 23055s that are mounted on the heatsink. So I'll just give it a test just to confirm again. As you can see there, it's stuffed, so I'll switch that off. Just put the next transistor on and see what that's like. I think last time I replaced some of these transistors on a power supply, they were STs as well, which these are. So maybe they're not so good, the ST transistors. I always find the Motorola 23055s very good. Right, so we'll just give that a test, see what that says. Again, unknown faulty component. So obviously they're stuffed as per the measurements that we made earlier on. So we'll get some new ones out now and fit them, and next time I come back to it, it'll all be back together, ready to switch on. Right, we're just going to check for short circuits. We put some new 23055s in, some nice RCA ones from the good old days, and there's a mica washer under each transistor, and as well as that, then there's this insulating plastic thing which is all one piece. It insulates the legs, as well as it's got like a through collar which goes through into the heatsink to prevent the bolts from shorting to the heatsink, because this obviously got 26 volts on a supply by these two red wires here to the bolts. So the bolts are insulated through the heatsink, and then the bolts themselves make electrical contact with the shells of the transistors, which are the collector leads. So we just got to make sure that we don't have any short circuit. So I'll just got my meter on ohms there. So what I want to do, I want to get a good electrical connection into that screw thread there on the heatsink. And then if I just go on to the tab here, we shouldn't be getting any resistance there. Likewise on that tab as well. And then if we go between the tabs themselves and the shells of a transistor, so this is where it gets interesting. Just go onto the shells of a transistor themselves, and then onto the tab. We should get a connection, which we are. And then likewise on this one here, onto the shell of a transistor, if I can get on it. There we are, got a short there. Now likewise we shouldn't have any shorts between the leads going through the holes in the thing. It's always worth checking this, because I have had cases in the past where sadly due to rushing reassembly you can end up with the leads touching the heatsink in certain places, and then it can cause untold problems. So nothing short circuiting there. So I can reattach these leads then to the transistors and then reassemble it. So I've got an assortment of transistors in here anyway, so plenty of spares there. But these ST things, they never seem to last, these. I don't know why, just the way it is. Anyway, get it reassembled and Bob's your uncle. Okay, so the moment of truth has arrived. If everybody can cross the fingers while we hit the switch. I've got it plugged into mains. I've put the lid back on without the screws just in case it goes fizz bang and flames and smoke and components start flying out. I don't want an electrolytic capacitor wedged in my forehead. So we've left that on. We've got the output of the power supply connected into the meter at the back. Obviously we might have to adjust something if it does work, that little potentiometer on the board, to get it to 13.8 volts DC, which it indicates. So yeah, so fingers crossed, here we go. Wow, there we go, look, 13.28 volts. It sounds good to me. So no smoke yet or fizz bangs or anything like that. So we're not out of the woods yet though, because we need to load test it. I've got some quite juicy resistors here that we can use, some big boy resistors, to load the output so that we can draw about 10 amps DC on it. So we need to check that and leave it running for a bit to see if it warms up. So that's looking good. I'm very pleased with that. It looks like as if that repair has been successful, but as I say, we'll do the load test, because I've had it before where you've done load tests on things and then it's gone bang. So let's do that first. Let's check that out and adjust the power supply accordingly. Right, back soon. Okay, so we've adjusted this trimmer down here. There's a little trimmer just there, this thing. A bit of a devil to twiddle, but I managed it. We've got it 13.8 volts now. So next thing to do is just to load it, and I've got a selection of these power resistors and things, you know. And we'll load it. We'll start with about 3 amps and then work us way up. But you have to be careful with these, because remember, as a teenager messing about with these when I was learning electronics, you know, we're about 12-year-old, 10, 11, 12, something like that. And I had some of these, and I think I bought them from Tandy, Radio Shack, back then when they were about. And they weren't as big as these though, I don't think. I think they were sort of more that size. Yeah, it were one of these, that size. Anyway, I connected my probe, my power supply to it. Now we're just doing calculations of current and resistance. Anyway, this thing got really hot, so hot that you could, you know, like an electric bar fire. And I noticed the end cap here starting to walk its way out, and I observed it just ever so slightly starting to creep out. And anyway, it got so far and it went bang, just like a gun being fired, and the end whoosh, shot off, it hit the wall at the other side of the room. It whizzed across just as fast as a bullet, left a mark in the wall. I always remember that. And the test leads that were soldered, I'd soldered the connections to the end of each of the terminals of the resistor, and it ripped the cable in half. It literally just like getting the wire and pulling it so tight that it just breaks, and it broke the wire off the end of the terminal. So that's the sort of force that it came out with. And I think some of these, maybe it depends on the manufacturer. It's only happened to me once. I think there might be trapped air in them, you know, when they're made, or they have little air bubbles and things. But it's the expansion of the air inside as the metal brass sort of heatsink bit heats up to super high temperatures. The air expands inside, it pushes these caps off. I always remember that. It went boom, and that was that. So you've got to be careful with these. You've got to mount them on a heatsink reel if you're going to use them for long periods of time when they get hot. But for this little test we're doing, it'll be okay. Okay, so we've got our resistor set up now, and we're ready to test it. I'm going to test it around about half its duty cycle, half its rated current, which is 5.5 amps roughly there. And if we see there, we've got 5.5 amps being consumed. Just interested to see the voltage. So it drops down to 13.3 volts then from 13.8, which I think is more than adequate. And I'm just touching, those resistors are getting quite hot now, yeah, that's warming up quite nicely, is that, so don't want to over egg it, but yeah, feel the heatsink at the back, moderate warmth, just starting to come through on the heatsink, just mild warmth. So yeah, we've got a fair bit of current going there, 5.5 amps. So I'm quite happy with that. I'm not going to progress with that test any further now. I think we've proved the point that the power supply works. So yeah, that's a good result. That's a good result. So I think we'll put the screws in and fasten it back up. There's not much we can do about the case, I'm afraid. I might put some glue on the sides there that are cracked where the screw hole fastens through, because I think it's been dropped or banged at some point. And we'll take it from there, I think. See how it goes once it's back together. Might have to glue it maybe with some hot snot around the side possibly, and then put the case on to try and keep it fastened in, or put some capstan tape round the outside edge, whichever. So see how that goes anyway. Let's get all the screws back in. Okay, so we've got the scope of truth behind. What I've done already, I've set a measurement up on the oscilloscope, so that basically what we're going to be doing is we're going to be looking at the power supply when it's under load, the output ripple. So it's currently at 5 millivolts per division on channel 1 with AC coupling, and we're going to look at the supply output and its ripple while it's under load. In order to do that, obviously we've got the resistors, which we've got here, and there's a few of them. So these connected in that fashion provide about 6 amps load current. So what we're going to do, we're just going to switch the supply on, and we're going to connect these terminals up, and what we're going to do is we're going to watch the birdie and see what ripple. Now that noise that you're seeing there is just electrical noise in the workshop that the pro's picking up, because we're a very low level there of sensitivity on the oscilloscope. And the idea is that if the electrolytic capacitors in the power supply are on the way out, or the tired, we'll get an enormous amount of ripple when it's under load, which is something you won't see when it's off load. So the object of this test is to just look at that and analyse it. Now, we shouldn't be getting more than, say, a couple of 100 millivolts ripple when it's under severe load, until, you know, obviously it reaches a point where it's saturated with load. But this is a sort of 6 amp test, 50% duty cycle if you like, and we're just measuring that on the scope. So I'm going to connect the power now, obviously here, so we can measure that with the oscilloscope, and here we are. So this, as you can see, there's a tiny little bit of ripple there, which at 5 millivolts per division, it's just slightly higher than 1 division, 1 graticule. So it's round about 6 or 7 millivolts that on that ripple, which is the waveform you can see superimposed in the noise, and you can sort of see the 50 Hz, 100 Hz ripple there coming out with what is essentially from the bridge rectifier. So yes, that is very good, is that? I don't, as you can see, there's hardly any ripple there at all, you know, so that's good. Very pleased with that indeed. Yeah, I'm very happy with that. I don't see any problem there whatsoever. I'm just going to disconnect this because those resistors will start getting hot, and the heatsink at the back's warming up there. So I'm very pleased with that test. I think that proves now that the supply is ready to go back to the customer. We put some capstan tape around the front panel there in order to glue the front on, if you like, because it's cracked in 2 places and the lug at the side's missing. So this tape goes all the way around, and it's got a very good adhesive composition on it, and it's heat proof tape as well, so it'll not come off with temperature. So that'll make sure the front's secure, provided it's not bashed. But yeah, very, very strange little power supply. That's certainly been a bit of a challenge at times until we got the circuit diagram. Admittedly, I would have been, you know, up the creek without a paddle had we not found the circuit diagram, because of those resistors which had failed and they'd burned out. So obviously there was no way in a month of Sundays we were ever going to get the value of those, and in which case it might have come down to trial and error, trying different resistors and just trying to see if we can get it going. But it wouldn't be the same, to be honest with you, unless you knew what value resistor to go in. Yeah, so that's another thing about it. Again, strange design, having that sort of soft start power up pulse to get it going into regulation. It's just a very odd design for such a small power supply. I'd question this as well about the current rating, you know, being sort of 10 amp constant and 12 amp surge. I think that's way overrated for the supply. I think the supply itself is not capable of delivering 10 amps constant by any stretch. It doesn't have fan cooling. The heatsink at the back for the 2N3055 power transistors is only small. There's no way that could sink, you know, the amount of wattage required at 10 amps at 13.8 volts through that those two transistors, and it maintain its output for long. It'll probably melt down before anything, but yeah. So I mean, 5-6 amps may be continuous, and even then not for long. You know, it depends what your version of continuous is, but you know, half an hour of 5 amps being drawn on this, you'll be able to fry an egg on it, so it'll probably just burn itself out. But you know, for 10 amps, 12 amps sort of at short durations, probably okay, but nothing major, not 10 amps constant. It's just not capable. I'm very surprised at the output as well not being protected, because normally you get crowbar circuit on there, so that if the voltage, say, gets above, say, 15 volts or something, because of the fault condition, it'll short the output and crowbar it. So therefore it'll blow the fuse or protect itself, or it'll bring a relay in to disconnect the output, whatever. There's no diode protection either on the front terminal, so should back EMF occur when you've got long cable connections coming off the front, if it were to short circuit, the back EMF would blow some of the components inside or damage it. And also causes damage to other pieces of equipment. And on that note as well, when you think about it, this customer may have had this on a bench powering up expensive equipment, and obviously when that fault conditions occurred, this could have blown up very expensive equipment simply because there's no protection on the output. There's a big difference between 13.8 and 26 volts, so that could have blown up something quite expensive. So this is the trouble with these sort of power supplies that are not designed in the same mind as perhaps other models. Struggle to understand why in the design for the 50 amp version they're using 50 rectifier diodes, when surely, you know, the object of a design when designing power supplies to keep the component count down to minimum, because you're reducing the cost, so you use minimum components required for your design. And I think they've over-egged the pudding with this. To have that soft start circuit, and then, you know, the 2N3055s effectively get started with a pulse, and then the output of the 2N3055s are actually captured into a Zener diode regulator, which then keeps the regulation loop in lock. And it just seems a bit strange to me that most other power supplies of this sort of output would normally use a fixed voltage regulator to drive the 2N3055s, or indeed an adjustable voltage regulator, LM series, where it has all that circuitry that we're seeing on the board integrated within the IC itself, and it has fallback current protection as well, and other features. So I just don't understand why they've gone to all that trouble with all these Zener diodes and resistors, transistors here, there and everywhere. Could have done away with all that, really. And yet they've gone to all that extreme of having this soft start and this weird thing around the regulators, and yet there's no protection on the output. It seems like they've gone so far and yet stopped short of a real problem that's going to occur when the output here goes to 25 volts. And it seems so strange as well, the way that they designed the circuit for that, for such a low current power supply. Just seems strange to me. Anyway, that's just my opinion. But anyway, I think we'll finish the video here. If you like the video, please subscribe, helps the channel, and there'll be more videos like this to come with repairs such as this, so keep your eyes peeled on the channel. And by all means, leave comments below if you have any comments on this particular repair, any others. And thank you very much for watching, and we'll catch you again. Bye for now, take care.